Hello dear students. So today we will discuss the second part of this chapter, that is periodic trends in properties of elements. The first part we have completed, which was based on periodic table related to the elements, their nomenclature, position of elements, and modern periodic table. So the next part we will discuss certain properties which may be physical and chemical properties. First our focus will be on physical properties, and we will try to explain how these properties they vary as the number of electrons or we move or we analyze the periodic table, how these properties they tends to change. So first will be trends in physical properties, and these physical properties they will involve atomic radius along with ionic radius or ionic radii, ionization enthalpy, electron gain enthalpy, and electron negativity. So these will be the physical properties which we will discuss, and then after analyzing these properties we will go through the periodic table, how these properties they tends to vary. The first one is atomic radius. The main property, atomic radius. As you are aware about radius, the distance from the center to the outermost point in the circle or somewhere. In this case we will discuss this with respect to atom, but as you know that the size of the atom is very small and it's very complicated to measure its radius. It is of the range, the size of the atom is in the range of 1.2 angstrom, or we can say 1.2 into 10 to the power minus 10 meters, which is very small. And the second one is that the electron cloud, as you can see in this picture, the electron cloud, it doesn't have specific boundaries. So these two things they make it difficult to calculate the exact or precise value of atomic radius. So it is very difficult to calculate precise value. There are certain ways by which we can calculate the radii, and as per that atomic radius has been divided into three parts, mainly covalent radius, metallic radius, and van der Waals radius. So in order to analyze this atomic radius we will go through these one by one. So the first term of atomic radii which can be expressed, that is covalent radius. This is one of the practical approach to estimate the size of an atom of a non-metallic element by measuring the distance between two atoms when they are bonded together by a single bond in a covalent molecule. For example, if we look in this picture, there are two atoms and these atoms are bonded by covalent bond. Once a molecule is bonded by covalent bond, so the distance from the center, this is the center of this atom, and to the center of adjacent atom, again they should be bonded by covalent bond. This internuclear distance between two atoms which are bonded by covalent bond is called as covalent diameter. Now once we get this covalent diameter, from this covalent diameter we can predict the covalent radius. And how it can be calculated? That is, covalent radius will be half of this covalent diameter, means this part. That will give us covalent radius. For example, chlorine molecule is given. That means two atoms are combined. They are bonded by covalent bond. The distance from the center to the of one atom to the other atom, that is its covalent diameter, it is 198 picometer. 198 picometer. And now what will be covalent radius of chlorine atom? So covalent radius will be 198 divided by 2, that is 99 picometer. So half of the internuclear distance between two atoms which are bonded by covalent bond is called covalent radius. Another way of expressing atomic radius is metallic radius. Metallic radius which is taken as half the internuclear distance separating the metal cores in the metallic crystal. In this diagram to the right side, metallic crystal is given. The atoms, they are in close packing, right? The minimum space is left vacant in between. So this is metallic crystal. In this metallic crystal, any two atoms which are adjacent, which are joining each other, if we take their nucleus into consideration, for example this and this one, so these are two adjacent atoms in metallic crystal. So the distance from, as you can see through this blue line, the distance from the center of this atom to the another atom, this will be called as metallic diameter. Again, metallic diameter, if we take into consideration these copper atoms, this metallic diameter for copper atom, it comes out to be 256 picometer. From this we can calculate metallic radius, and it will be metallic radius of copper in this case will be 256, that is metallic diameter divided by 2. So again it is the half the internuclear distance separating the atom cores in the metal crystals, right? So metallic radius is metallic diameter divided by 2. Okay, so example is copper, which has metallic radius of 128 picometer. After going through two terms for determination of atomic radii, now we will analyze how atomic radii it varies in periodic table, that is across the period and down the group. What will happen to the size or atomic radii? So first of all, across the period. So if we analyze this first table, two periods are given, second and third period: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. These are second period elements, and third period elements are given: sodium, magnesium, aluminium, silicon, phosphorus, sulfur and chlorine. Likewise, their atomic radius is given. For lithium, it is 152 picometer. For beryllium, 111. Now if we carefully analyze this trend along the period, so it comes, you will observe that the size or radius goes on decreasing. Fluorine has the smallest atomic radii. In the same manner, if we analyze the third period, again the trend is same. From sodium, which has 186 picometer, it continuously goes on decreasing, and chlorine has 99 picometer. So atomic radius goes on decreasing across the period. Now the question arises that why there is decrease in atomic radii. So in order to explain this, just analyze this size of the elements are mentioned. Now for example, lithium, as you can see, it is bigger in size than beryllium, and then beryllium is bigger than boron, carbon, nitrogen, oxygen, and fluorine is smallest. Just neglect the 18th group, we will discuss it later on. So up to 17th group, right from first group to 17th group, in every period the radius goes on decreasing. Okay, so this is general trend of atomic radii across the period. The decrease in atomic radii across the period can be explained on the basis of addition of electrons within particular atom or element. In this case, period 2 elements are shown: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and their electronic representation is mentioned. For lithium, atomic number 3, the electrons are present. This is K shell, first shell, and this one is L. So we are talking about K and L shell, outer shell is L. So electrons can be represented as 2 in first and 1 in second. For lithium, this is the outermost electron, there is only one electron. Now when we move from lithium to beryllium, this is beryllium, For beryllium, the electronic representation will be slightly different. That is, in first shell there will be 2 electrons, but in second shell, as compared to lithium, there is one additional electron. The same electron get added in the L shell, right? So L shell has now 2 electrons. So that means on moving across the period, the electron entry takes place within the same shell. For example, for boron, the representation will be 2, 3. So 3 electrons are now there. In the same manner, for carbon, 4 electrons will be there, 1, 2, 3 and 4. For nitrogen, 5 electrons, 1, 2, 3, 4, 5, so on. For fluorine, there will be 7 electrons in the valence shell and 2 electrons in the inner shell. So due to entry of electrons within the same shell, nuclear charge, or we call it as effective nuclear charge, this effective nuclear charge, it increases. What is the difference between nuclear charge and effective nuclear charge? So nuclear charge is just simple attraction from the nucleus to the valence electron, but effective nuclear charge is the difference between the nuclear charge and shielding effect. Now what is this shielding effect? Shielding effect or screening effect, it is the obstruction of the inner electrons. If we take this structure, this arrangement, now 1 electron is present in the inner shell, that is in first shell. In the same manner, 1 electron is present in the outer shell. Now the electrons which are present in the inner shell, they carry negative charge as well as the electron in the outer shell. So inner shell electrons, due to that similar charge, they tends to repel the outer electron. They tends to repel, and hence the force of attraction decreases slightly. Okay, so this difference, that is whatever attraction would have been there if there is no inner electron, it would have been stronger, but now due to this shielding effect, this net force of attraction goes on decreasing. Now the net force of attraction which is experienced by the valence electron is called as effective nuclear charge. I hope you got it. So nuclear charge minus screening effect is called as effective nuclear charge. Okay, nuclear charge minus screening effect will give you effective nuclear charge. Now due to increase in effective nuclear charge, what will happen to the radii? Radii goes on decreasing. So that's why along the period, atomic radii or size goes on decreasing. Now how atomic radii, it varies in the group. When we move down the group, atomic radii increases, or the size of the element that goes on increasing. If we analyze this group 1, lithium is given sodium, potassium, rubidium, cesium, francium. So you can see that the size goes on increasing as we move downward, right? And the reason, it can be due to addition of, can you see the difference, that there are 2 shells, K and L. Now K, L, M. For sodium there are 3 shells, for potassium 4, 5, 6, and for francium there are 7 shells. So basically it's due to addition of new shell which overcomes the increased nuclear charge, hence the size goes on increasing as we move down the group. You can see the difference, the addition of shell, 2 shells are there and now there are 7 shells, 1, 2, 3, 4, 5, 6 and 7 shells. So basically downwards atomic radii increases due to addition of shell. Do remember, nuclear charge, that also goes on increasing, but the effect of magnitude of addition of shell dominates the nuclear charge. So these are the general trends for atomic radii.